Welcome, folks. I want to give an analogy between group homomorphisms in abstract algebra and linear transformations in linear algebra. So if you're watching these videos, you're learning about abstract algebra. Maybe you've heard about linear algebra before, maybe you haven't. Either way is fine. Some of these images that I'll draw, in my opinion, are some of the main messages of linear algebra that you want to keep in mind, either after you've taken linear algebra classes or before or during linear algebra. Okay, so let's say I give you a matrix. A matrix is just a rectangle of numbers. Okay, so here's some matrix. Okay, this matrix has size 2 by 3, because there's 2 rows and 3 columns. Okay. The wrong way to think of a matrix is just as this rectangle of numbers. It's not so interesting. The right way to think of a matrix is you should think of it as a map, in this case from 3D space to 2D space. Let's give a name to this matrix. Let's call it M. Okay. So matrix M is a map from 3D space to 2D space. And the way this map works is you take an input vector, x1, or maybe we'll call it xyz, and you map it to matrix multiplication, that matrix times this vector. Okay, so let me show you one example. Let's say I have some input vector. I'll make it very easy. Maybe it's 0, 1, 1. Okay, so I have some point in 3D space. Where does it get mapped? M times xyz, in this case, is the matrix M times 0, 1, 1. So let's write it out. I take this vector and I lay it down horizontally here, and then I multiply the corresponding entries and add them all up. So I get 0 times 2 plus 1 times -1 plus 1 times 3.5. In this case, this just gives me -1 plus 3.5, which is -2.5. And then I take this vector and I lay it down here. I get 0 times 7 plus 1 times 2 plus 1 times 4. And in this case, that just gives me 2 plus 4, which is 6. Okay, so that's how I sort of take some input here and I map it to some output there. Maybe that's a better dot for this particular input. All right, so the rules of how that's done are you either know them or they don't really matter, but we're mapping from 3D down to 2D. Matrices always give linear maps. So we don't map things in squiggly ways, we map things in very linear ways. Okay. So let me talk about possible maps, maybe I should say linear maps, from 3D to 2D. Okay, and I think I'm going to have sort of three classes of maps. I'm going to have the maps that are rank 0, the maps that are rank 1, and the maps that are rank 2. Okay, so every map, from 3D down to 2D is going to fall in one of these categories. All right, so I'm mapping from 3D to 2D in each of these cases. And I want to draw a picture. Okay, so rank 0 means that when you map 3D in, what you hit is just the origin. Okay, so all of 3D gets squashed down to the origin. I'm going to shade everything here in red because this is what gets mapped to the origin, and everything gets mapped to the origin. Okay, so not a very interesting map. Everything just gets collapsed to the origin. Makes me think of a black hole or something. A rank 1 map maps down to a line. Okay. And when you map down to a line, it's like you're taking 3D and you're squeezing it down to a line. So what gets collapsed down to a single point? An orthogonal plane. Okay. So what gets mapped to the origin here? The thing that I shouldn't have said the word orthogonal, but what gets mapped to the origin is a plane. So there's some plane. Maybe I'll draw it like this. Let's try again. There's some plane that gets mapped down to the origin. Okay, and when you take parallel versions of that plane, you see what gets mapped down to every other point. So what gets mapped down to this green point? Well, it's this parallel plane. And when you ask what gets mapped down to this orange point, it's this parallel plane. Okay, so 3D is divided up into these parallel planes. Every parallel plane gets mapped down to a point. And then the image is this line. Okay, the last possibility when you map linearly from 3D down to 2D is that you hit all of 2D space. So what you hit is everything. And still you can ask what gets mapped to the origin. All right. When I map 3D down to 2D, if I hit everything, I'm still collapsing lines. Okay, it's almost like I'm taking 3D and I have all these parallel lines and I collapse each line down to a single point. Okay, so there's some line here, maybe it's, I don't know, this line that gets collapsed down to the origin. And if you ask what gets mapped to this green point, it's some parallel line. And if you ask what gets mapped to this orange point, it's some parallel line. Okay, so parallel lines all get collapsed down to single points. All right, so in purple on the right-hand side, I've sort of drawn the image of the linear map. I've drawn everything that gets hit in 2D. So I hit either the entire 2D space, or I hit a line, or I hit just this single point. And then in red on the right, on the left, I've sort of drawn the kernel of the linear map. I've drawn the things that map to the origin. So here a line maps to the origin, here a 2D space maps to the origin, and here all of 3D maps to the origin. Okay, so let me wrap up by making the analogy to group theory. When you take your input space and you quotient out by the kernel, you get something that's isomorphic to the image. Okay, so take all of 3D, quotient down all of 3D space. This kernel is all of 3D space. So collapse this entire 3D space down to a point. So when you take 3D space and collapse out all of 3D space, you just get a single point. So the input space modulo the kernel sort of gives you a single point. It's like the Rank-Nullity Theorem. You know, the rank is 0, so the nullity is 3, which is saying that the kernel has to be 3-dimensional, if you've heard of the Rank-Nullity Theorem. Okay, here, take all of 3D space and quotient out by the kernel, which means quotient along these parallel planes. And when you do that, each plane gets collapsed to a single point, and you're just left with a line. Okay, so we've taken our input space, quotiented out by the kernel, and we've got the image. Finally, in this last picture, take all of 3D space, quotient out by the kernel, which is, you know, this red line. And when you take 3D space but collapse this family of parallel lines, you just get a plane that results. So the analogy with group theory is the following. If phi is a homomorphism of groups, then what you can do is you can take the input group, quotient out by the kernel of this map. We haven't defined quotienting one group by another yet, and you get the image of phi. Okay, so these pictures are all examples of that, but they're in this particular case of linear algebra where things are very visual. So the image is in purple here, and the kernels are in red here, right? And in this class, you know, this first isomorphism theorem that it's called, you know, an input group mod, the kernel of a homomorphism is equal, or maybe I should say isomorphic to the image of the homomorphism. Here in abstract algebra, it's a very algebraic theorem, right? But in linear algebra, this is a very visual theorem, and it is oftentimes how you think of linear maps from one space to another. Okay, so that was a high-level connection. I hope some of that intrigued you, and certainly no worries if the details didn't make sense. But it's nice when you play with math and then you're able to put it in your own language, which for me is often a little bit of a visual language, despite the fact that abstract algebra is often quite symbolic. Any public questions? All right, thank you.